In this question, we were shown a table and an object seated on top of the table. The table is frictionless, and the object is going to feel two different pushes. One push which is pointed like this, and a second push which is pointed like this. For the sake of clarity, I'm going to call this push applied force 1, so let's call it FA1, and this one I'm going to call FA2. The mass of this object is 10 kilograms, and FA1 and FA2 both have sizes of 30 newtons. Now, let's draw a free body diagram. This object is going to feel the force of weight pointed downwards. It's going to feel a normal force pointed upwards. There's no friction to take care of, so the only two other forces it's going to feel are their two applied forces. So we have our first applied force, FA1, and our second one, FA2. Now that we've gotten this far, these are now all of the forces that are acting on this block, so we are ready to set our axes. The easiest way to do this is to set the x-axis to be in line with FA1, the y-axis to be in line with the normal force, like that. Now, as far as FA2 goes, this FA2 now becomes the only force that is not in line with one of our axes. It's at an oblique angle. And specifically, we were told that it was 30 degrees below the horizontal. So that means we need to break it into its two components, the horizontal component and the vertical component. And to be particularly rigorous about it, this angle is actually negative 30 degrees because it's below the x-axis. So the vertical component is opposite this angle. So this now is going to turn into FA2 times the sine of negative 30. By contrast, this component over here is in the x-axis and it is adjacent to this angle. So this is now going to become FA2 cos of negative 30. So now that we have all of this information, we've now broken FA2 into its components. We are now ready to find out what is the total force acting on this. Now, our object is not collapsing into the surface, and it's not levitating from the surface. So there's no motion at all in the y direction. Additionally, there's no friction to worry about. So that means that we can get away with not even calculating what's happening in the y direction. So the y direction includes the normal force, the weight force, and the sine component of FA2. So that just leaves FA1 and the cosine component of FA2, and those would represent the total force acting in the x direction. So in the x direction, we have total force is equal to FA1 plus FA2 cos negative 30. But total force is also equal to mass times acceleration. So we can say that FA1 plus FA2 cos negative 30 equals mass times acceleration. Now let's plug in for everything that we know. FA1 is 30 plus FA2 also 30 cos of negative 30 is equal to mass 10 times the acceleration, which is the only unknown here. So let's go ahead and solve this out. (30 plus 30 cos 30 gives us 55.98. And when I divide both sides by 10, I get an acceleration of 5.598 meters per second squared. And because this acceleration is in x, I can say I hat. So that is our solution. That is the acceleration of the box as it is pushed by these two forces. In this question, we have a bird which is sitting on a wire like so. That is the limit of my drawing abilities. You guys are already used to that. So, if we were to look at this bird, the bird has a weight which is pointed down, and it is supported by two symmetric wires on either side. In the first part of this question, each wire is deflected downwards by 5 degrees. So let's say that I call this tension 1, the left wire, and this one tension 2, the right wire. So the bird is supported on the right by tension 2, and on the left by tension 1. Now, one thing to be careful of is that the mass of the bird was 0.026 kilograms. They told you 26 grams, but we do all our calculations in kilograms, so we have to divide by 1,000 to get the right mass. This is now the full free body diagram, and we are now ready to set our origin and axes. The origin would be on the spot, which represents the bird, and the axes would be as follows. I'm going to set my y-axis along the weight, like that. And I'm going to set my x-axis like that. So already what I see is that we have two tensions which are both pointed at oblique angles. In fact, if we were to follow it out, these would both be 5 degrees. You can prove that with a little bit of geometry. So this is 5 degrees. And this is 5 degrees, which means that really the orientation of this force vector is 180 minus 5 degrees, which is 175 degrees. Now, let's break T1 and T2 into their corresponding components. Let's start with T2. T2 has a horizontal component and a vertical component. The vertical component would be T2, this is the opposite side, so this would be T2 sine of 5 degrees. This is the adjacent side, so this would be T2 cos of 5 degrees. What about T1? This opposite side would be T1 sine of 5 degrees. And this adjacent side would be T2 cos of 5 degrees. Now, let's proceed to solve for the sizes of these two tensions. We'll start by solving for the tension in the x direction. Or more correctly, I should say, let's solve for the forces in the x direction and see what balance we get. Now notice there are two unknown variables, so that means we need to solve two different equations. And as you probably guessed, one of them will be determined from x and the other one from y. So in the x direction, the total force is given by the force pointed right, that's T2 cos 5 degrees, minus the force pointed left, this would be T1 actually, cos 5 degrees. But we also know that total force is equal to mass times acceleration. So T2 cos 5 degrees plus negative T1 cos 5 degrees is equal to mass times acceleration. And we can simplify this still further, because the bird is not accelerating in the x direction. The bird is standing perfectly still, or sitting perfectly still. But that means that the acceleration is 0. So this entire right side becomes 0. And this now simplifies down to T2 cos 5 degrees minus T1 cos 5 degrees is equal to 0. Now, just for the sake of rigor, I'm going to calculate what the cos of 5 degrees is. 0.996. So we can rewrite this as 0.996 T2 minus 0.996 T1 equals 0. And if I were to divide everything by 0.996, then I would get T2 minus T1 equals 0, or equivalently, T2 equals T1. And that makes sense. You expect these two tensions to be equal to each other because this is an absolutely symmetric question. It's sort of like the nicer version of the ball on 2 wires question that I gave in the video. So yes, this is the first relationship that we have between our two tensions in our 2 wires, that the two tensions are equal to each other. So using this information, we will now turn to what's happening in the y direction now that we've solved for everything that's happening in x. Now let's figure out what is happening in the y direction. The total force in the y direction is represented by 3 different forces. One is T1 sine 5 degrees. The second is T2 sine 5 degrees. And the third one is the weight, which is pointed downwards, which I would write like something like this. The total force is equal to mass times acceleration. So we can combine these forces with Newton's second law to find that T1 sine 5 degrees plus T2 sine 5 degrees plus the negative weight. And all of that's going to be equal to mass times acceleration. Now again, the bird is not moving, so that means that the acceleration must be 0, which means the entire right side becomes 0. Now, let's find out what the weight is. The weight of the bird is given as mass times gravity. Mass 0.026 times gravity 9.81. That works out to 0.255. So that's the size of the weight. So now T1 times the sine of 5 degrees, actually why didn't I work that out to? 0.087. Plus, and I'll just write this the same way, 0.087 times T2 minus the weight, 0.255, is equal to 0. So let us simplify this. I can move the 0.255 to the other side, and we end up with 0.087 T1 plus 0.087 T2 equals 0.255. Now, we can simplify this still further by applying this equality, which we found out from the y direction, T2 equals T1. So let's plug in T1 over here. We get 0.087 T1 plus another 0.087 T1 equals 0.255. So, what's 0.087 times 2? 0.174. So 0.174 T1 equals 0.255. And so the last step is to divide both sides by 0.174. And we get 1.46. So T1 is equal to 1.46 newtons. That's the size of the tension in the left side of the string. And since we know that T2 is equal to T1, the tension in the right side must also be 1.46 newtons. The second part of this question is sufficiently different that I want to start it over from scratch. So here we have a wire. We have the same bird as before, but this time the deflection of the wire is considerably less. It's 0.5 degrees on both sides. And the mass of the bird is 0.026 kilograms. Now, let's draw the free body diagram. There is the weight pointed down. There is the tension, which is pointing off in this direction. And there is the tension, which is pointing off in this direction. As before, I will call this one T1, this one T2. And that would correspond to the entire free body diagram. Now next, let's draw the origin, which is set at the bird, the spot, and now let's draw in the axes. This way is x, and this way is y. The angle being formed by T2 is going to be 0.5, and the angle being made by T1 is also 0.5. So, let us break the tensions into their components. Like so. And like so. The horizontal component of T2 becomes T2 cos 5 degrees. The vertical component would be T2 sine 5 degrees. Comparison, the T1 would be T1 cos of 5 degrees, since this is the adjacent side. And this one would be T1 sine. Oh, why am I saying 5 degrees? It should be 0.5 degrees in all of these places. So, somewhat more messily than I had hoped for, but 0.5 degrees is the angle for both of these. And we can solve this rather similarly to how we solved the previous version. So let's start in the x direction. In the x direction, the total force is the x component of T2 cos 0.5 degrees minus T1 cos 5 degrees. But total force is also equal to mass times acceleration. So, T2 cos 0.5 degrees minus T1 or I suppose using the way I like to write it, as t1 cos 5 degrees, or 0.5 degrees, is equal to mass times acceleration. But this bird is not moving in the y direction. The acceleration is 0, as is the entire right side. Now, as for the cosine of 0.5 degrees, we have 0.99996. So let's actually write that whole thing. We now have 0.99996 T2 minus 0.99996 T1 is equal to 0. Divide both sides by 0.99996 and you get T2 minus T1 equals 0, or T2 equals T1. So this is our first relationship, identical to what it was in the earlier part of this question. Now that we've solved for the x direction, let's see what's happening in the y direction. So in the y direction, the total force is equal to T1 sine 0.5 plus T2 sine 0.5 minus the weight. But total force is in turn equal to mass times acceleration. So when we combine everything, we get T1, I really should stick to my own rules, T1 sine 0.5 plus T2 sine 0.5 plus the negative weight is equal to mass times acceleration. Now, our bird is not moving in the y direction, so that means that the acceleration is 0. So we now have T1 sine 0.5 plus T2 sine 0.5 minus weight equals 0. So now we need to find the weight. Weight is equal to mass times gravity. Mass, 0.026. Gravity, 9.81. .255. So now we have solved for the weight. Now we can say that T1 times sine of 0.5 is 0.00872. So 0.0087 T1 plus 0.0087 T2 minus weight 0.255 equals 0. But T2 equals T1, so I can plug in for T2 over here. 0.0087 T1 plus 0.0087 T1, since T2 and T1 are the same thing. And I'll move the 0.255 to the other side. So 0.0087 times T1, that gives, if I double that, I get 0.0174. Now let's do 0.0255, sorry, 0.255 divided by this value, 14.61. This is in newtons. So that is the size of the tension in this left cable. It's considerably larger than what we got in the first part of this question, where it was only about 1 point something newtons. This is almost 10 times larger. And T2 has the same tension. In this question, we have a 120 kilogram box that is sitting on the floor, and we are going to start pushing it like so. The coefficient of static friction, remember that static friction is what you have to outdo if you want to start something moving, is 0.5. So that is the relative slipperiness between the bottom of this box and the rough floor. The coefficient of kinetic friction, that's the friction that you need to outdo to keep something moving, is 0.3. So now that we have our picture, let's start drawing our free body diagram. The box is going to be subjected to weight force pointed down and the normal force pointed up, so those two are already quite familiar. There is the applied force coming from our push, and finally there's the friction force which we are trying to overcome. And in this case, this would be static friction, because in the first part of this question, we are getting this object moving. We're starting to move this object. So now that we have all of this information, we can now get started on drawing our axes. I'm going to set them in the usual way. I set x to be in this direction, the positive x to be in this direction, and the positive y to be in this direction. And to review what the question was asking, we want to start this moving, and we want to find out what's the minimum force applied we need to provide. The minimum force applied is going to depend on what is the maximum value of static friction that is possible. You need to overcome that maximum value in order to start it moving. So that'll tell you what your force applied needs to be. So now that we have our axes, let's start off by solving what's happening in the y direction. We have to do this because even though the object is not moving in the y direction, it's not collapsing downwards or levitating upwards, we have a force of friction here. And whenever you have a force of friction, that force of friction depends on the normal force, and that's why you have to solve for the normal force first. So we need the y direction. In the y direction, the total force is given by normal force pointing up minus the weight force, which is pointing down. But total force is also equal to mass times acceleration. So we get normal force plus negative weight is equal to mass times acceleration. Now, we need to find out what the weight is. The weight is given as mg, mass 120, g 9.81. And that works out to 1177.2. So now we have the normal force minus 1177.2 is equal to mass 120 times the acceleration in the y direction. But this thing is not moving in the y direction, so that means that the acceleration is 0, which means that this entire right side cancels out, and moving 1177.2 to the other side, I get a normal force, which is equal to 1177.2 newtons. And because this is in the y direction, this would be j hat newtons. Now that we've solved for the normal force, we need to use that to find the force of static friction. Now, in the x direction, there are two forces. there is the applied force, and there's the force of static friction, which is pointing in the negative direction. But the total force is also equal to mass times acceleration. So that means that applied force minus the force of static friction is equal to mass times acceleration. So how big is the force of static friction? It's equal to mu static multiplied by the size of the normal force, which is 0.5, we were given that in the question, times the normal force, which is 1177.2. Which is 588.6. So that means that the maximum value of static friction, I really should write it like this. The maximum possible value of static friction is 588.6 newtons. It can take on a value that's less than that, but it can never take on a value that's more than that. So if we want to be able to start this moving, we need to apply at least that amount of force. Because if we were to say that applied force minus 588.6 is just going to start it moving, then that implies that the acceleration has just become a little bit more than zero. So I could write it as 120 times an acceleration of 0, which means this side is going to cancel out, which means that the applied force is now going to become 588.6 newtons. And since we're pushing it in x, that should be I hat. The next part of this problem was to look at what happens after you've started it moving. Now, once you've started it moving, you're no longer in the realm of static friction, you're in the realm of kinetic friction, which means we need a new free body diagram. So, normal force points up, weight points down. Obviously, those two things have not altered at all. The applied force is also the same as what it was before. What has changed is that we now have kinetic friction, a friction that applies once you have started something moving, a friction that applies when two objects are sliding across each other. Now, in this situation, the weight force was already calculated as 1177.2 newtons. The normal force we've already calculated as 1177.2 newtons. The applied force we calculated just a moment ago as being 588.6 newtons. And the kinetic friction is the only unknown over here. So now, let us put a set of axes on this question. We use precisely the same axes as before. And now, let us solve for the kinetic friction. The total force occurring in the x direction, and we will only focus on the x direction, there's no point in solving the y direction, because there's still no acceleration in this y direction, nothing interesting is happening there, and we've already solved for the normal force which is needed for the friction. So we'll only focus on the x direction. The total force is given by the applied force minus the force of kinetic friction. But total force is also equal to mass times acceleration. Therefore, applied force plus negative force of kinetic friction is equal to mass times acceleration. I almost forgot. Remember that the applied force is the same as what it was in the previous part of this question, because once we have gotten this started moving, we are using that same force to keep it moving, and we want to see what acceleration results. We need to solve for the kinetic friction. That's equal to mu sub k multiplied by the normal force. Now, the slipperiness of the two surfaces, when this is in motion, mu sub k is 0.3. Times the normal force, which is 1177.2. Which works out to 353.16. So that's the size of the kinetic friction. Let's take this information and put it into the force balance. Since we know the applied force and the kinetic friction, the only thing that's unknown is this acceleration. So, applied force, 588.6, minus kinetic friction, 353.16, is equal to the mass, 120, times the acceleration. 588.6 minus 353.16 gives us 235.44. So 235.44 is equal to 120 times the acceleration. So divide both sides by 120 and we find the acceleration. 1.962. This would be in meters per second squared, and since it's in the x direction, we have to put an I hat there. So this is the acceleration of the box once we have started it moving, and once we are in the weaker realm of kinetic friction rather than static friction.